Hello, Professor Sargent here with you again. Going to talk about the multiplication principle and then some special cases called permutations and combinations. Suppose you go to a fancy restaurant and there are, for children, 3 appetizers available, which for lack of imagination, I'm going to call that set of appetizers A1, A2, and A3. And then there are 4 entrees, i.e. main courses available. Again, for lack of imagination, E1, E2, E3, and E4. How many orders are possible? One approach would be to make a tree diagram, which is based on the branching of decisions that are made. So I imagine that the waiter or waitress would go around and first ask about what they want for an entree, and there are 3 choices. And then the decision tree branches again when they come back around and ask what they want for the main course. So there are going to be 4 choices. If the first appetizer has been chosen, there's going to be 4 choices if the second appetizer was chosen. And there are going to be 4 choices if the third appetizer was chosen. If you look at how many endpoints we have to this branching, there are 12 of them. Now, by the way, my preference would be, since this is happening in order, ordering the appetizer first and then the entree, my preference would be to list the different choices as ordered pairs instead of a tree diagram. So what I'm going to show here is all the ways that the first appetizer could have been chosen. Oh. Followed by all the ways that the second appetizer could be chosen. And finally, all the ways that the third appetizer could have been chosen. Either one of these approaches, this may be something that you might have seen when you were very young and your teachers were trying to lead you to multiplication. For example, we see 4 choices here, 4 choices here, 4 choices here, suggesting 4 plus 4 plus 4, or better yet, to get to that 12 more quickly because of the repeated addition, 3 times 4. So what we just saw there was an application of the multiplication principle. If we had also been asked about selecting a dessert and we knew how many ways there were to do that, then you could consider, first of all, the choosing of the appetizer and entree, put that together as one task, and the choosing of a dessert as another task, so that we would find out how many ways there are to do all 3. Well, instead of thinking of it that way, we can just say that we can generalize the multiplication principle to any number of things that we wish to do, or any number of tasks. So if you have m ways to do a task and you know how many ways to do each, then multiply how many ways there were to do each to find out how many ways to do all m things. So in a similar question, we're told here that kids can choose just 1 dish, 1 dessert, and 1 drink. There are 5 main dishes, 4 choices, 4 desserts, and 6 drinks available. So by the generalized multiplication principle, we would have 120 different meals possible. In number 10 here, also apply the generalized multiplication principle. We're going to start with a letter, and that letter cannot be A. So that's going to leave us for the first task 25 options, and then we need 4 digits. There are 10 digits. However, that 4th digit must be non-zero, so that would leave us 9 choices there. And so that's going to give us 25 times 10 cubed times 9. 25 times 10 cubed, which is 1,000 times 9. 25,000 times 9 is 250,000. I want to say, let's see. I typed it wrong anyway. If I multiply by 10, that would be 250,000. So I suspect 225,000. And that's what I get on the calculator. Okay. Now what next? For the moment, I'm going to skip over talking about factorials and go to a special application of them. Factorials are where you have n things available. You arrange all n of them so that you would be multiplying that integer n. It's a positive integer, and you multiply it by all the other integers prior to it on down to and including 1. In that case, arrange. There are some different words we could use for arrange. Arrange, put in order, ranking. Hierarchies are suggested, like the hierarchy of a company: president, vice president, treasurer, secretary. There could be a hierarchy to that. So if we have 4 things available and we want to arrange 2 of them, first of all, that is a permutation. I think of permutations, order. You've got O for order and P for permutation right next to each other in the alphabet. And if I didn't know about the multiplication principle, I could put these as ordered pairs. Here's all the ways that A could be the leader of the 2. And then let's see here, all the ways that B could be the leader. All the ways that C could be the leader. And all the ways that D could be the leader. Notice besides the order in permutations, just like factorials, there is no repetition. You're not going to have some ranking where A is getting repeated. You're not going to have A as both a president and a vice president, for example. Excuse me. Now, if we think of this like the multiplication principle, some books use P42, 4,2. Other textbooks use 4P2. They are the same. This is what we find on the TI-84. And let's see here. Okay. Without a calculator, because there are two things to arrange, I would say in terms of the multiplication principle, there are 4 tasks to complete. So we're going to have 4 for the first. And because we're putting this in order and there's no repetition, 3 choices for the second. So 12 ways, just like what we saw here. On this one, P5, 3, or in other textbooks, 5P3, you want to take of those 5 things, arrange 3 of them. There are 3 tasks to do. Pick your first, pick your second, no repetition, and pick your third. So there's going to be a total of 60. I'm not going to try to list 60 ordered triples, although if I can remember, I'm going to show something that would suggest how we could come up with that a little later in the video. On the calculator, fire that up and show the TI-84. First off, real quick, before I show the calculator, there are 2 formulas for figuring out permutations. One of them involving factorials. The other looks like this, where the last thing that you multiply by is n minus r plus 1. In this case, 4 minus 2 is 2, 2 plus 1 is 3. Coincidentally, 5 minus 3 is also 2, 2 plus 1 is 3. Okay, so in this case, the last thing we multiplied in each of those cases, the last thing in this string of multiplication was 3. I do not like to use the formula for permutations that involves factorials, and here's why. Factorials get very large very quickly. You can get a factorial by pressing the math key, and then on older calculators, it might say PRB instead of PROB, but in any case, should still be your 4th choice. 250 factorial is huge. It cannot calculate a number that big. But what I can do instead is type the 4 first, and then the math key again, the probability submenu, choose number 2, and we get 12. By the way, let me check something here. I'm going to put it in math print mode. There's a math print mode. It actually will look like what I wrote on the board as 4P2. Then 5P3, I said should be 60. So there we go. All right, so following that, let's take a look at number 11 here. Little League team has 20 teams entered into some like World Series of Little League. How many ways can there be a first, second, and third place? Is it a permutation or a combination? It is a permutation. I know that because there is an order to this: first, second, and third. They're not just saying how many ways could we have a top 3 out of the 20. We specifically want to know first, second, and third place. Furthermore, there is no repetition. No team is going to be both in first and third place. So there would be 3 blanks to put in here because we want to pick the top 3 teams. And from that, start off with 20. So you've got your first place team. See, besides writing the blanks, it's a good idea to describe what you're doing for yourself. Second place and third place. Out of those 20, Once you've picked the one that is first place, well, not pick, but they play the game and we find out, then you use up one of those teams. There's only 19 remaining, and followed by that, 18 left for third place. Now I'm also going to type in 20p3 on the calculator to see what we get. But let's see, 20 times 18, 2 times 18 is 336. So 20 times 18 is 360. Multiplying it by the 19 in the middle would be the same as multiplying it by 20 minus 1. We'll distribute. 36 times 2 is 72. So 7,200 minus 360. I believe we're going to get 6,840. Let's see if that's what comes up on the TI-84. Here we go. So 20p3. If I can get it to wake back up. There we go. All right, I've already got something arranged 3. So if I insert there 20, I have to delete that 5. 6,840 as predicted by hand. So what next? Okay, just recently I had computed 5p3 was 60. Now I did not try to list 60 ordered triples. However, what if we were to pick from these 3 things, but order did not matter? I claim that there are 10 ways that we could pick a triple where order does not matter. And then we'll talk about the connection between this versus this. I could pick A, B, and C. Notice that I'm putting the curlicue braces there because order does not matter. The parentheses would be suggesting an ordered triple. This is an unordered triple. I could choose A, B, and D, or A, B, and E. I'm pretty sure those are the only ways I could have both A and B in there. Let's see here. How about A, C, and D, A, C, and E. Then let's go with B, C, and D, B, C, and E, C, D, and E. So far, I have 8. Give me a moment here. I need to think. Pause this. Okay. Sometimes it's easier to keep track. Instead of from the 5 picking the 3, you can think of which 2 have been left out. So here I left out D and E. Here I left out C and E, C and D, B and E, B and D, A and E, A and D, A and B. So when I look at this, I see these 4 are all the ways I could leave out E and somebody else. I should be able to similarly come up with 4 ways to leave out D and someone else. Here's one of them. Here's another. A third. and a fourth. So now let's see how many ways I've left out C. Here's 1, 2, and looks like that's it. So what I've missed leaving out was both AC and BC. Continuing, B then should show up in 4 places: here, 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 and now here. And A should show up in 4 places: here, 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 and here. All right, so leave out AC. That's going to give me B, D, and E, which, double checking here, was not anything I had already listed. BD, this has BD, but A, not E. Remember, order does not matter. Okay, and then leave out BC. That should be my 10 ways that I could pick from 5 available, pick 3, no repetition, but order does not matter. Furthermore, I'm not going to write all of these, but if I were to take that unordered triple ABC and put them into order, we're going to get 6 ways that that one can be put in order. Start off with A and then reverse whether B or C, or is it C follows, C follows B or B follows C, or start off with B and then reverse the last 2, or start off with C and then reverse the last 2. For all of these 10, I could come up with 6 ordered triples, which is 3 factorial. So there were 10 unordered triples, but if I multiplied by 6 to find out how many ways to put them in order, I would get that 60. What I'm getting at is that this is talking about pick 3 things, talking about a combination. In a combination, there is no repetition, but order does not matter. With a permutation, there was no repetition. So that applies to both. But with a permutation, order mattered. With a combination, there's no order. Okay, so what we have just found out then is that the number of combinations in some textbooks as CNR, or in others NCR, which is the way it shows up on the calculator. We have found out that 5C3 is 10, and there's a formula involving the factorials. The one I prefer is to find out how many permutations there are and then divide by R factorial. If I went from that 60, divide by this, that's dividing out the ordering of the triples to get 10 unordered triples. As a matter of fact, if I had not done this earlier, and I had to compute this by hand, well, cancel out the 3's. 2 goes into 4 twice, and dividing by 1 doesn't matter. So 5 times 2 is 10. And let's confirm that on the calculator. So type your value for n first, and then math and the probability submenu. This one is our third option. And we had to pick without repetition or order 3 things. There's 10. Now, also notice this. Now, earlier we had both seen from 4 things, picking and arranging 2 of them, that there are 12 ordered pairs we could come up with, comparing that to a special case of the multiplication principle. We also came up with 12. So what I am suggesting with NCR equaling NPR divided by R factorial, I'll pretend I didn't do this here, then for C2, when there are 4 things available and you want to pick 2 without arrangement, how many combinations are there? We have 4 times 3 over 2 factorial, so 2 times 1. Do some reducing there. 2 times 3 is 6. Well, try to back that up. When order does not matter, those 2 are the same. AC and CA are the same. AD and DA are the same when there is no order. BC and CB, BD and DB, same. And CD and DC. Again, notice the use of the parentheses for the ordered pairs versus the curly Q braces for the unordered pairs. Okay, so checking for C2 on the calculator here real quick. Let's see if we're getting 6 that way as well. Gotta wake it up. 4C2. There we go. All right. Well, let's build on that. In how many ways can an investor select 3 mutual funds for her investment portfolio from a recommended list of 10 mutual funds? You're not arranging those 3. You're just picking those 3 out of the 10. So we're looking for 10C3. By hand, $10C3 would be equal to 10P3 divided by 3 factorial. 3 blanks top and bottom. Up here, starting with 10, down to 9, down to 8. And by the way, a reminder, 10 minus 3 is 7. 7 plus 1 is 8. In the denominator, 3 factorial. 3 times 2 times 1. I'm going to do some reducing. Having that 1 in there is not going to change anything. 3 into 9, 3 times. And it doesn't really matter which even number I use the 2 with. So I'm going to go for getting a smaller number. 8 times 3 is 24. 24 times 5 is 120. Let's check out whether the TI-84 agrees that 10C3 is 120. So here we go. 10C3, wake up. Okay, 10C3, 120. It's all good. Continuing a little bit further. Let's say we have 10 seniors and 5 juniors in a business club at a high school. How many ways can you pick 2 seniors and 3 juniors to be going to a conference in Denver? Well, it's like we're building a committee to go to this conference. Committee combination. There's no ordering of who is attending that conference. What we need to do is pick from our 10 seniors, pick 2 of them, and from our 5 juniors, pick 3 of them. So I'm starting off first with an application of the multiplication principle. Ten seniors, we're going to choose 2, and 5 juniors, choose 3. 10, 2, 5, 3. This is picking the seniors. That's one overall task. And this is from the 5 juniors, picking 3 of them. Again, no repetition, no order. So by hand, I would have 10P2, which is just going to have 2 dashes. Divide out the ordering by 2 factorial. Here I'll have 3 dashes. Divide out the ordering of 3 times 2 times 1. Start with 5 here. Some reducing. Well, 2 into 10 5 times. Cancel the 3s. 2 into 4 twice. So I've got 5 times 9 is 45 times 10. Coming up with 450. This is the main thing, to recognize how many ways could we choose without repetition and without order. From the 10 seniors, pick 2 of them. From the 5 juniors, pick 3 of them. And then we're getting into the nitty-gritty of the arithmetic after that. Let's see if the calculator agrees on this one. Ten C2, 10C2. Come on. Times 5C3. Don't know if this is going to work, but 450. That's what I came up with. I'll say we take that a little further. Either we have the 2 seniors from the 10 and the 3 juniors from the 5, or 1 senior and 4 juniors. Well, the or should be telling us to add, choose 1 senior and 4 juniors. By the way, why do I know I can add? That goes back to the fact that you have disjoint subsets or disjoint events. You cannot for that one conference at that one time, both pick 2 seniors and 3 juniors, and at the same time, 1 senior and 4 juniors. Okay, so we're going to be adding to that 450. Well, there's only one blank, and dividing by 1 factorial is kind of boring. Here we're going to have 4 blanks. Divide by 4 factorial. Starting off with 5 up in the numerator. The 4 3 2s can cancel. 5 divided by 1 is 5. So 10 times 5, I'm coming up with 50. Total of 500 then. The biggest thing there, if you understood the previous example, was the or was telling us we're doing something very similar over here, and then we're adding them up. So let's see if indeed we take that previous answer and we add to that. Let's see here, previous answer plus, now it was 10C1. From 10, choose 1, no repetition and no order, and so multiply. From 5, choose 4 with no repetition and no order. And it works. We're going to take a moment here to look at 2 special cases. The first is what to do when you have n things available and you want to arrange r of them. Let's say we're going to arrange all of them. If we can tell the difference between each of them, then there would be n factorial ways. That, by the way, is npn. npn is the same as n factorial. But what if we can't tell the difference between some of the things being arranged? Or at least in terms of what we're paying attention to, indistinguishable. So remember 3 factorial or 3p3, that is equal to 6. Let's say that we're going to arrange the letters from the word B, and we can't tell the difference between the 2 E's. Then either I could put the B in front, or I could put it in the middle, or I could put it at the end of the 2 E's. So we have 2 places where the 2 E's are right together, either both at the end or both at the beginning. And then the other case is where the B's are in between. But what if we are distinguishing between them with a red and a purple E? Then over on the side, we're going to see that we could flip the order of the red and the purple E's. That would give us our total of 6 when we have 3 distinct things, and we're going to arrange all 3 of them. 3 factorial is 6. Let me go back for a moment there. Okay. So the idea here is if we cannot distinguish between some of them, what you would do, similar to how I explained going from permutations to combinations, we were dividing out the order. Here, we would do 3 factorial divided by the product of, we had a total of 3 objects. 2 of them, we could not tell the difference. Also, we had the B, 1B. So we'd figure out 3 factorial over 2 factorial times 1 factorial. And that gave us the 3 ways to arrange that we saw at first without the coloration, without the E's being distinguishable from each other. Let me scroll back to that again. So they were right here. Okay. So A similar question then would be as follows. Let's say that we want to find out how many ways to arrange the following letters. Took a moment there to try to think of a word that would not typically get used for one of these examples. The typical one is radar. Well, okay, civilization. There are 5, 9, 10, 12 letters in here. C only shows up once. I shows up 4 times. L once. Z once. A once. O once. And N once. So we're looking for 12 factorial because all the 1 factorials are 1 and multiplying them. Okay, we're going to have 4 factorial in the denominator, which I could try to bother to do that by hand by writing out 12 on down to 1 and then 4 down to 1 and cancel out the 4 over 4 times 3 times 2 times 1. But I'm not going to get that very quickly anyway. So on the calculator, let's see here. Okay, 12 factorial divided by 4 factorial. Oh, typed that wrong. Delete that. There we go. Pretty large number. Let's do one more of those. In the word mattered, we have 8 letters. M shows up once. A shows up once. T shows up twice. E shows up twice. And then R and D both show up once. So again, 1 factorial is 1. Multiplying by the ones down here are just going to leave us with 2 factorial times 2 factorial. And let's see here. I know 5 factorial is 120. 6 factorial is 720. I'm going to, since 2 factorial is 2 times 1, both of these are 2. So 2 times 2 is 4. 4 into 8 is 2. And 7 times 720 is 5,040. So I'm looking for 2 times 5,040, which should be 10,080. Let's check that out. Again, we're not going to really need to worry about putting in the 1 factorials there. So let's see here. Eight factorial. Delete that one. This time we're dividing by 2 factorial and another 2 factorial. We should put in some parentheses here. Oop, not the curly Q braces, but parentheses. There we go. Insert once more. There's our 2 in front of the factorial, and we're multiplying by another 2 factorial. So here we go. Darn it. I got rid of the 2. 2. Math key. Probability submenu. Factorial. 10,080 as predicted. And one more special case here in just a moment. Suppose that we want to arrange 3 things, but this time it's not a linear arrangement like in a row of seats in the classroom. Suppose it's around a table. And we know 3 factorial is 6, but I've color coded these. Hopefully it's showing up. A is in purple, B is in blue, and C is in green. Out of those 6 in a linear arrangement, 3 of these are going to be the same. If I put A here and then B here and then C up here, the reason this is the same is because when A looks to the left of A, that's going to be C, and to the right of A is B. All we've done is rotated, but their arrangement is the same. You could say we've rotated by 120 degrees, and another 120 degree rotation would give us C over here, and now A is here, B is up here. But once again, A looking to the left is going to see C, and A looking to the right is going to see B. So what would be something different? We could have A up here and then B over here. It's not showing up all that well. Let me put B in black here. Okay. And C in green right here. Now when A is looking to the left, it's going to see B. A looks to the right and sees C. And our 120 degree rotations this is the same as this. And similarly, A, then C up here, and B down here. All 3 of these are the same as that first one. Because again, A is looking left to see B, A is looking right to see C, A looks left and sees B, A looks right and sees C. In all 3 of these. It was reversed what they saw on the left and the right in the first set. So that 3 factorial, that's not what we're getting. We're only getting 2, which happens to equal 2 factorial. To illustrate this a little bit further, it may not be the best animation, but give me a moment here. My claim is that if we have 4 things to arrange, but in a circle instead of a line, instead of 4 factorial equaling 24, we're going to have 3 factorial giving us 6. So this animation is probably something that I'm going to wish to redo. What I did was color-coded the seats that they're in. And again, I'm asking the question of who's left of A, who's right of A, who's straight across. And you should see 6 different arrangements of those colors. Anything else, you'd be rotating the people. In this case, by 90 degrees. So instead of 4 factorial equaling 24, we're only going to get 3 factorial or 6 arrangements of 4 things. 4 things available, arrange all 4, but this time it's in a circle. And that's all I've got. I hope this helps.